Hello everybody. I would like to show to you today power measurements on a symmetrical arranged bipolar Tesla coil, and want to compare that with a asymmetrical bipolar Tesla coil. I will give you only a brief description about all the technology here in use. I will go into much detail in a report I will provide on my professional website. That's a company which deals with the results of R&D of the open source and has already started working in collaboration together with others. On this site, which I will post soon, you will find then much more details as I can cover here in the short video section, which I want to keep only to a certain length to keep your attention span. So we're gonna have in part 1 here the symmetrical arranged bipolar Tesla coil with no capacitors on each side on a secondary connected directly to load. In part 2 I will do exactly the same measurements, but in an asymmetrical arrangement of the primary to the secondary based on the golden mean ratio. I will compare then both results to each other and draw the conclusion. So this video of power measurement for this both coil types is not to show you that we have a lot of energy gain here. It is an extension of the golden ratio video to show you that an asymmetrical configuration will yield a much higher power output. So we're going to move on to the load and all the details. So that is the standard load. It's a fluorescent bulb, so power rating is not really relevant, and I used it very often in the last 2 years, so it's completely nugget. And I want to show you some inconsistencies and power fluctuations at specific frequencies which I cannot explain exactly, but I will go later to that. So what we got to do here is we measure voltage on both sides. So we have here high voltage Agilent oscilloscope probes with extreme low loading, 7 picofarad. So I use 2 of them, 1 of each side. What it gives me is, it gives me a voltage propagation based on the frequency on each side, and that will become apparent. It's quite interesting to see what's going to happen. We use on a so-called low side, we use the P6021, a current probe. Here in that example I have grounded it. Normally you would do a so-called floating measurement without grounding. However, the floor noise is very high here in my garage. So the floor noise need to be subtracted from the calculation later on. So the floor noise is literally the result of all electromagnetic radiation, RFI radiation, within a living environment, like a power supply somewhere here, any kind of power lines going somewhere, and that has an impact. And because I'm connected already to the big coil with my probes, I'm picking up quite a lot of power fluctuations. So if I zoom in here, you can see that I have set up the system peak to peak as a main measurement. This peak to peak measurement will have to be normalized later on. So we average it, give it down to a mean value, and then I go even further down and apply RMS. So I have to, the square root of 2, I have to divide the values, and later on that counts for voltage and counts for current. You have also to apply here so-called differential measurement. What is differential measurement? A differential measurement is when you take two measurements from a load or the device under test, DOT. You take the measurement on the load, on the wire, and you do the measurement outside of the load, close to the load, and you get a value, and this value needs to be subtracted from the value from the current. What you do by doing that is you're removing the ambient or the radio frequency radiation or the electric field energy by keeping it plain and simple only on a level which goes through the wire. So that's quite complex. You have to do that here. We do that here for voltage, and we do that here for current, for each value. That means for each frequency I have to do literally two measurements, inside and outside of connectivity. Put that in a spreadsheet and have to subtract that for further calculation later on. I think I mentioned I wanted to make sure that I do it all accurately. I measured 4 times the whole set, and I can tell you that there is a difference in measurement between day and night. I account for that as well. It's not a big difference, but it's visible in the power consumption and in the power output, and I normalize that as well.
You can see the fluorescent bulb and the transient energy spikes coming through as flashes. So these brief flashes are a tremendous amount of energy going through the system. I was previously not in a position to say how much energy it is or what's going to happen here. Now I'm very precisely in a position to measure this kind of transient in any system. So when I move over to the oscilloscope, I can demonstrate that and show you that. So we will have a standard value here. Take 2.2 kilovolt, let's say channel 2, 261 Hz. Now I freeze the frame. It goes about 400 volt down, 1.870, but the amps are at about 1.021. So if I multiply that, let's just assume out of curiosity for Ohm's law, the standard value before was about 600 watt. The spike value is about 1.9 kilowatt, 3 times as much energy as there was before. The input power does not change at all. So that's quite curious, and I will investigate that further, will change different loads and so on, see if that happens. Only at specific frequency in a low value it happens. In higher values it doesn't happen at all anymore. It stays stable at the same value. Up first here the spreadsheet with consolidated rows. That means the rows in which something happens. You see the different columns I have here, and the rows are showing only the interest in frequencies. So you see on the left hand side the frequency, then there is light, so I register as well if the fluorescent bulb is illuminated or not. Then you have input power, then you have values of the driver, then you have voltage frequency. So what I have marked as red on the voltage side, or purple is, you see, is when the voltage is equal on both sides. So on the right hand side you see something marked on COP orange. These are my peak values, which I will show then in the power chart. So you have the input power here and your output power, and the ratio between them is the COP coefficient over performance. 444 I have not on here, but I will have that on my power chart. So going over to my next chart will be the voltage chart.
Here you see the plotted voltage chart for both ends of the bipolar Tesla coil. So red stands for the north pole or the right hand side, blue stands for the south pole or left hand side. So you would expect from a symmetrical arranged bipolar Tesla coil that the voltage would go up and down both on both sides, but funny enough that is not the case here. So you see that the north pole or the right hand side always dominates, even if it's arranged in a symmetrical fashion. So we're gonna move on, and I will show you now the power chart, how does that translate in energy. You see the plotted chart of the power propagation. So the red line represents the power output, the blue line represents the power input. At the beginning at 1 kHz we have around 16, 17, 18 watt. It goes down and comes down to 1.5, 1 watt. I added here also the spikes, the transient spike at 44 kHz, which after normalization, differential measurement and RMS is going down to 1000 watt, and compares that to the input power of 3.35, gives you a COP of 618 as a transient. As the overall winners, let's say, I have two markations for COP 44 and COP 52. One is about 64 kHz, the other one is about 198. These are not harmonic values. That means they are not symmetrical in the voltage propagation on both sides. They are asymmetrical as well. And another thing, when you go back to the chart, you will see that at both sides on highest value the fluorescent bulb is not illuminated. Also very important to note. Marks already a very strong indication that asymmetrical configuration is much more powerful. Even if the arrangement of coils is symmetrical, there's a natural balance towards asymmetrical values, or the golden mean.